So in this slide for quantum, we are going to discuss about second part in motivation. So regarding the quantum computing, its simulators, working principle, architecture, and so on. So in previous session, we have discussed about definition and quantum gates. So here we are going to see about Moore's law, quantum mechanical effects. So first one is Moore's law. So this graphical depiction states the evolution of number of transistors per node year-wise. So in 1975, we holded with 2 power 10 power 4 number of transistors in a computational node. So year by year or decade by decade, it is showing a gradual increase in number of transistors, which is indirectly representing how the computational environment is going to be complex for solving the real world problems. So this is scaling up in 15 to 20 years, which is a scale which is called to be as a drastic scaling. So quantum mechanical effects occurs at this scale. So measuring a state that is called a position disturb it. Quantum systems sometimes seem to behave as if they are in several states at once. So different evolutions can interfere with each other. So quantum mechanical effects, additional nuisance to overcome or new type of behavior to make use of. So Shor is a philosopher who has stated something in 1994 that polynomial time algorithm for factoring the integers on a quantum computer. So this algorithm is mainly dealing with polynomial time. So this could use to break most of the exciting public key crypto systems, including RSA, elliptical curve crypto. So in 84, Bent probably secure codes with short keys. So also with quantum information, faster algorithms for combinatorial search problems have introduced. Fast algorithms for simulating the quantum mechanics has been intruded in the computational world. Communication savings in distributed system has introduced. More efficient notion of proof systems has an inclusion in this quantum world. Quantum information theory is a generalization of the classical information theory that we all know, which is based on probabilistic theory. So this is a circle which is representing a core classical information theory and which is held with a superset of quantum information theory. So one qubit is represented by means of vectorial form. Vector in two-dimensional complex vector space, which is called to be as a Hilbert space, is called in quantum computing field. So this is a Dirac notation where column vector is called as ket and row vector is called as bra. Dual vector, which is representing transpose and complex conjugate, is also represented as bra. Realization of qubits. There is a nuclear spin which is positive and negative. There is a polarization of photon which is going to represent left side and right side. There is an electronic state which is going to reflect the grounded or excited level. A bit versus a qubit. A bit can be in two distinct states, 0 and 1. A measurement does not affect the state. A qubit can be in a state or in a state other than a linear combination of the basis state. When we measure the qubit, we find it. So with a probability, we are representing it as two cases, kit with 0 level, kit with 1 level. So next, this figure is depicted as Boch sphere. It is a representation of one qubit. A qubit in a superposition state is represented as a vector connecting the center of the Bloch sphere with a point on its periphery. The two probability amplitudes can be expressed using Euclidean angles. So this particular circle, when it is going to be rotated, the ket and a bra angle is going to make a transpile effect with z-axis, y-axis and z-axis, which is going to reveal half 0 and half 1, which will be viewed as either 0 or 1 or half 0 or half 1 based upon the reader's view. So this is the qubit representation and measurements. So 1 bit, 1 qubit, possible states of 1 qubit before the measurement, after the measurement. Figure option A is representing a simple depiction of reflecting 0 and 1 with yellow color solid dot, and 1 qubit is represented with basic logical state of 0 on top, 0 1 on below. So we are assuming a cylinder which is holded with n number of uh, angles, circular angles. Each and every connected point is representing a superposition states. So after measurement, each and every qubit is going to hold n number of superposition states. So this is a 2-bit representation. So 0 superposition and uniform superposition. Whenever we are going for 0 superposition, top layer will reflect the 0 kit and bottom layer will reflect the 1 kit. Uniform superposition is going to reflect the proximity which is going to be carried throughout the circles. Measuring the two bits. Before measurement, the state of the system consisting of two bits is uncertain. It is given by the previous equation and the corresponding probabilities. After the measurement, the state is certain. It is 0, 0, 0, 1, 1, 0, 1, 1. Like in the case of classical 2-bit systems. Measuring the two qubits. What if we observe only the first qubit? What conclusion can we draw? We expect that the system to be left in the uncertain state because we didn't not measure the second qubit that can still be in a continuum of states. The first qubit can be 0 with probability, 1 with probability, which is represented as 0, 0, 0, 1, 1, 0, 1, 1, like normal logical gate with 2-bit representation where n is represented with n is equal to 2. This is called to be as a bell state. So which we have seen as a ball, it is called to be as a bell. So square root of 0 kit plus square root of 1, which is going to have a summation. Measurement of qubit in a state gives 50% of time with logic 0, 50% of time with logic kit 1. So 50-50 chances in the bell state on top and below. On top the bell state will have kit 0, on bottom the bell state will hold kit 1. Quantum gates. Quantum gates are similar to classical gates, but we do not have degenerate output. That is, their original input state can be derived from their output state uniquely. They must be reversible. This means that deterministic computations can be performed on a quantum computer only if it is reversible. Luckily, it has been shown that any deterministic computations can be made reversible. So this is a 1 qubit representation with simple two values of for n. Here the bracket is represented with a notation which is termed as a Bloch notation. So it is reflecting the formula where the options is going to reflect the superposition states. 1 qubit gates. This is the identity gate which leaves a qubit unchanged. X or NOT gate, which is a transpose which is reflecting the components of the input qubit. Y gate, it is also gate. Z gate flips the sign of the qubit. H is a Hadamard gate. So classical and quantum systems, these are the probabilistic states with 3-bit representations: 000, 001, 010, 011, 100, 101, 110, 111, 2 power 3 is equal to 8 possibility of answers which can be presented either with a bell state of 0 or 1 or half 0 or half 1 state. So these are all the quantum states where we are going to fix the amplitude for the frequency of photon, what we are going to transpose. This is termed as a Dirac notations. These are the basic vectors which is going to hold the column and row vector. So your formula is summation of your amplitude plus the value of the ket, either in terms of 0 or either in terms of 1, which is going to throw the value of your brag. Thank you. We have seen what is Bell state, what is Shor algorithm, who is the philosopher, and we have studied the probabilistic state, and we have seen the difference between classical and quantum states in this. So hope learners, we have you have all listened the corresponding content which we have discussed in this particular session. Thank you all.